Hey everyone, welcome back. I am TreeJunt, and this is Visual Lab. In the last lecture, we established one rule, and I want to make sure that rule is crystal clear before we go any further, because today, everything we build depends on it. We studied the stack as a data structure, not the memory region, the actual data structure, and we found that it has exactly one rule governing everything about how it behaves. Last in, first out. We used a cafeteria tray counter to understand it. 3 trays on the counter. You can only ever reach the one on top, the one placed most recently. The one placed first is buried at the bottom, waiting. You cannot skip to it, you cannot reach around it, you remove from the top, or you do not remove at all. The tray that went in last comes out first. That is exactly what last in, first out means. Now, do function calls behave the same way? If main calls multiply and multiply calls add, then add is the deepest function running right now. When add is done, it returns to multiply. When multiply is done, it returns to main. You cannot return to main while add and multiply are still running. The order is enforced. The function called last is always the first one to return. We saw the pattern, we named it, but we stopped there, and we left several important questions completely unanswered. How does the CPU actually make this happen? What exists in memory that enforces this order? How does a function know where to return? How does main's entire state survive while another function is running inside it? The answer to all of those questions is the same thing. Every time a function is called, the CPU and the compiler together create a structure inside the stack, a carefully organized block that holds everything that function needs to run and return safely. That structure has a name, the stack frame. And in this lecture, we are going to build one completely from scratch, so that by the end, you will understand every single byte of it. Before we begin, let me show you what we are working with today. On the left, the C code we are going to execute. 2 functions, main and sum8, about 11 lines total. Deliberately simple, because we want to focus entirely on what happens in memory, not on the complexity of the logic. In the middle top, the CPU registers panel. Registers are small, extremely fast storage locations that live directly inside the CPU chip itself. Not in RAM, not on the hard drive, directly inside the processor. The CPU uses registers as its working hands. Every calculation, every memory access, every function call goes through registers at some point. We are working on x86-64 architecture today. x86 is the instruction set that almost every desktop and server processor uses, and 64 means it operates on 64-bit values, meaning memory addresses and data are 64 bits wide. This is the architecture your laptop, your desktop, and most servers in the world run on. Now, x86-64 has 16 general-purpose registers in total, plus several special-purpose ones. That is a lot of registers. But we are not going to track all of them, because most of them are not relevant to the specific story we are telling today. We are tracking 9 registers on this panel, and seeing 9 does not mean the CPU only has 9. It means these 9 are the ones that will actually do something observable as we build this stack frame. The panel is split into 2 sections. The top section shows 5 registers that are active throughout the entire lecture: RSP, RBP, RDI, RSI, and RAX. The bottom section shows 4 more argument registers: RDX, RCX, R8, and R9, which will become active when we reach the calling convention, where I will explain exactly how the first 6 register arguments of our function get passed. I will explain every single register precisely when it becomes relevant. On the right, the stack panel. The upper portion shows the visible main context. The lower portion shows the sum8 call and frame context. You will notice the stack grows downward on this diagram, from high memory addresses at the top toward low memory addresses at the bottom. This is not a visual choice. This is how the stack actually works in memory on x86-64 architecture, the same architecture we just described. And I am here to connect all three panels to make sure that when one line of code executes, you understand every consequence in the registers, in the stack, and in the CPU's control flow. Let us begin. Before we touch a single byte of memory, I want to establish two vocabulary words that will appear on every single block we build today. These are not optional vocabulary. These are foundational. If you do not have these two words locked in, the rest of the lecture will be confusing. The first word is caller. The caller is the function that initiates a function call. In our example, main calls sum8, so main is the caller. It is the function that is currently running, decides it needs another function's help, and transfers control of the CPU to that other function. The second word is Callee. The Callee is the function that receives the call. In our example, sum8 is being called by main, so sum8 is the Callee. The Callee takes control of the CPU, does its work, and when it is done, returns control back to the caller. Now here is why these two words matter so much. When a stack frame is built, it is not built by a single entity. Some parts are built by the caller before the call happens. Some parts are built by the callee after the call begins. Understanding who builds what and why is the key to understanding the entire structure. Every block we add today will have an ownership label, either main, the caller, or sum8, the callee. By the end of this lecture, you will know not just what each part is, but who put it there, and exactly why. Now, before the first instruction of main executes, I want to establish something that most tutorials skip entirely, but that is absolutely fundamental to understanding how any of this works. The C code you see on screen, main sum8, the local variables, the function call, none of this exists at runtime. By the time the program runs, the compiler has already transformed every line of C into assembly language, a much lower level representation that the CPU can directly execute. Assembly language is a human-readable form of machine code. Each line corresponds to exactly one CPU instruction. No abstraction, no interpretation. Direct hardware commands. Here is what the compiler generates for our C program. You wrote a few lines of C. The compiler generated many more lines of assembly. And 3 of those lines, push RBP, move RBP RSP, and sub RSP 32, you never wrote. The compiler injected them automatically. We will examine exactly what each of those does very shortly. Now, where does this compiled assembly actually live in memory? To answer that, I need to show you the memory layout of a running process. When your program is loaded by the operating system, the OS allocates a dedicated block of virtual memory for that process. This is called the process memory. Every process gets its own isolated block. One process cannot read or write another process's memory. And that process memory is divided into 4 distinct regions called segments, each with a specific purpose. The code segment, also called the text segment, sits near the bottom of the address space and contains the compiled assembly instructions for your entire program. This is where the CPU fetches instructions from, one by one, as the program runs. It is read-only. The program cannot modify its own instructions at runtime. Above that is the data segment, global and static variables. Variables that exist for the entire lifetime of the program. We have none of those today, so this segment is effectively empty for our purposes. Then the heap, memory used for dynamic allocation, through malloc in C, or new in C++. The heap grows upward, from lower addresses toward higher addresses. We are not doing any dynamic allocation today either. And at the top, the stack. This is where stack frames live. The stack grows downward, from high addresses toward low addresses, which means every time a new frame is pushed, RSP moves to a lower memory address. This is why we draw the stack with high addresses at the top and low addresses at the bottom. The stack and the heap grow toward each other. If a program uses enough of both, they can collide. That collision has a name, stack overflow, that you will understand completely in a future lecture. Our entire story today takes place in the stack region. The CPU fetches instructions from the code segment, and those instructions build and destroy stack frames in the stack region. With that foundation established, let us start executing. Before the first instruction fires, I want to give you something, a map. Here is what happens to most people learning stack frames. They watch slots appear on screen, registers change, memory fills up, and it feels like the computer is just doing things. You are watching but not really understanding because nobody gave you the sequence underneath all of it. In the frame pointer-based Sys-V walkthrough we are about to use, an ordinary function call passes through the same 7 conceptual stages in the same order. See these 7 steps on screen. Step 1, argument setup. Step 2, call transfer. Step 3, Callee entry. Step 4, Prologue. Step 5, function body. Step 6, Epilogue. Step 7, return. This is your map. Every time something appears on screen from this point forward, a register changes, a stack slot appears, a frame gets built. I want you asking one question. Which step caused this? Not just, what is it? Why does it exist right now? We apply this map to main first, then to sum8. Same map, twice. By the end, nothing on screen will feel like magic. Here is something that trips people up quietly for years, and most courses never address it. When you run a normal hosted C program, the CPU does not begin at main. It does not. Main is not the true beginning. It looks like the beginning from inside your C source file, but that is a convenient illusion. What actually happens in the usual hosted model? The operating system loads your binary into memory, sets up the process, and transfers control to the program's entry point. That entry point is not main. It belongs to runtime startup code. Runtime startup code comes from the C, runtime, and toolchain. You do not write it in your source files, but it is in the final binary, and it runs before main. It sets up the runtime state your program depends on, prepares process arguments, performs the relevant C runtime startup work, and then, when it is ready, it calls main, like a regular function call. Same call instruction, same rules. Why does this matter? Because it means main has a caller above it. Main has a return address. In this hosted frame-based walkthrough, main goes through the same 7-stage call lifecycle we are using for every other function. So now, let's start main's execution and watch its stack frame get built step by step. Step 1, argument setup. For main in our model, there are no arguments to place, so this step completes immediately. Step 2, call transfer. Control transfers into main, and the call from startup code has already saved the return address, so execution knows where to resume after main finishes. Step 3, Callee entry. Control has landed at main right here at its entry label. From this point, execution begins. Step 4, the Prologue. This is where the stack frame is born. Earlier in the scene setup, I pointed at 3 assembly lines, push RBP, move RBP, RSP, and sub RSP 16, and told you we would come back to them. This is that moment. Now look at the assembly panel in our curated teaching assembly. These 3 lines are Main's Prologue. These 3 lines are not in your C source. In this teaching build, we are using them to model a standard frame building prologue placed before your first source level statement. Real compiler output can vary by compiler, target, and optimization level. This block is called the Prologue. In frame-based code, like the code we are modeling, the Prologue builds the stack frame before your source-level body runs. We are working in a frame pointer-based model. Here, RBP is treated as a fixed anchor for the current frame until the epilogue. You will feel exactly why that stability matters in a moment. 3 instructions. Let us go through each one. First instruction, push RBP. Right now, in our concrete address model, RBP holds the base address of Main's caller's frame, the runtime startup frame. The absolute hex values on screen are illustrative. The relative layout is the part that must stay correct. We are about to overwrite RBP to build Main's own frame, but if we overwrite it without saving it first, we lose the ability to restore it later, and the runtime startup code expects its RBP back when Main returns, so we save it first. Push RBP does 2 things simultaneously. It decreases RSP by 8, claiming a new slot at the current top of the stack, and writes the current value of RBP into that slot. See RSP drop by 8. The stack pointer moved to a lower address because the stack grows downward, and we just claimed 8 bytes. That slot is the saved RBP, the caller's base pointer, preserved inside Main's frame. In this model, we restore it from this slot when Main finishes. This slot also starts what is called the frame pointer chain. Every saved RBP inside every frame points back to the previous frame's base pointer. Debuggers follow this chain to show you a stack trace, the list of every function currently active. The chain begins here. Second instruction, move RBP, RSP. This copies the current value of RSP into RBP. That is all it does at the machine level. But what it means is, this position right here, right now, is the base of Main's frame, the anchor. From this moment, in this frame pointer model, RBP stays fixed until the epilogue. RSP will shift around constantly. RBP stays locked right here. And because RBP is fixed, everything inside the frame is accessed relative to it. Local variables will be at negative offsets below the base. Stack passed arguments from the caller will be at positive offsets above the base. That rule is the reason RBP exists. Third instruction, sub RSP, 16. Decreasing RSP means claiming more stack space. This moves RSP 16 bytes lower, carving out 16 bytes of reserve space below the frame base. See RSP drop. See 2 slots appear from nothing. Main has one local variable result, a 4-byte integer. In this Sys-V teaching build, the compiler model reserves 16 bytes, so the stack is 16-byte aligned at the next call site. Result uses 4 bytes. The other 12 are padding. The Prologue is complete. Main's stack frame now exists. 2 registers tell you your exact position inside it at every moment. You have seen both activate. I want you to have a deep grip on both because they will appear in every single step from here forward. RSP, the stack pointer. One job holds the memory address of the current top of the stack. It always points to the lowest currently used address. On x86-64, the stack grows downward toward lower addresses. Push something, RSP decreases. Pop something, RSP increases. The RSP always point at the live edge, the lowest byte currently claimed. RBP, the base pointer. One job holds the memory address of the base of the current stack frame, the anchor. The critical difference from RSP moves constantly throughout execution. Pushes, pops, call instructions all shifted. In this frame pointer model, once the Prologue sets RBP, it stays locked to that address for the lifetime of the frame. That stability is exactly why the frame's contents are accessed relative to RBP, not RSP. RSP is a moving target. RBP is a fixed reference point. See that badge on the result slot? RBP-4. That means start at the frame anchor, go 4 bytes downward. That is the slot. Every offset badge you see during this lecture works the same way. Step 5. Main source code starts executing. First line, int result. Here is something that surprises people when they first really think about it. This line does not create any memory. The slot at RBP-4 already exists. You just saw it appear when the Prologue ran. The compiler model decided at compile time that main needs space for one local 4-byte integer, and the Prologue reserved that space when it subtracted 16 from RSP. The slot was created before this line ever ran. What int result is? Does is give a name to a slot that already exists. From this line forward, the slot at RBP-4 is called result. And right now, result is uninitialized. The storage is real, the slot is in the frame, but no valid value has been written into it by your program. Whatever bits happen to be sitting at that memory address before, left over from previous use of this memory, that is what is in there. Uninitialized does not mean 0. It means not yet written with a valid value by your code. Now we reach the line that everything else in this lecture is built around. Result equals sum 8 of 10, 20, 30, 40, 50, 60, 70, 80. One function call. 8 arguments. Every slot that is about to appear on the stack, every register that is about to change, every frame that is about to be built and then destroyed. It all comes from this one line. We restart the 7-step lifecycle. Same map. This time for sum 8. Step 1, argument setup. Main, as the caller, must place sum 8's 8 values somewhere sum 8 can find them. Where exactly? That is decided by the calling convention. A calling convention is a contract, a formal agreement established before any code runs about the rules of every function call. Where do arguments go? Where does the return value come back? Which registers must each side preserve, which can be freely overwritten? Without this contract, nothing interoperates. Different compilers, different libraries, different files, they can all call each other because they all follow the same contract. We are using the System-V AMD64 ABI rules for ordinary integer arguments on Linux and Mac OS X 8664. On Windows x64, the calling convention is different. Under this ABI for ordinary integer arguments, the first 6 go into registers in this fixed order. See RDX, RCX, R8 and R9 activate on the register panel. These are the 4 registers I told you about in the scene setup that they would become relevant when we reached the calling convention. That moment is now. The order is argument 1 RDI, argument 2 RSI, argument 3 RDX, argument 4 RCX, argument 5 R8, argument 6 R9. Watch main, load them. Line 31, move EDI 10. The instruction writes 10 into EDI, the lower 32 bits of RDI. So the RDI slot on our panel now holds argument 1. One thing worth understanding here, our register panel shows the full 64-bit register names like RDI, but the instruction says EDI, not RDI. EDI is the 32-bit lower half of the 64-bit RDI register. We are passing 32-bit integers. INT in C is 4 bytes, so the compiler uses the 32-bit register names in the instructions. On x86-64, writing to a 32-bit register automatically zeroes the upper 32 bits of the full 64-bit register. That is a hardware rule built into the architecture. you will see EDI, ESI, EDX, ECX, R8D, R9D throughout this sequence. All 32-bit forms of the 64-bit registers shown on our panel for exactly this reason. Inside sum8, this value 10 becomes parameter A. Line 32, move ESI, 20. The instruction writes 20 into ESI, the lower 32 bits of RSI, so the RSI slot now holds parameter B. Line 33, move EDX, 30. The instruction writes 30 into EDX, the lower 32 bits of RDX, so the RDX slot now holds parameter C. Line 34, move ECX, 40. The instruction writes 40 into ECX, the lower 32 bits of RCX, so the RCX slot now holds parameter D. Line 35, move R8D, 50. The instruction writes 50 into R8D, the lower 32 bits of R8, so the R8 slot now holds parameter E. Line 36, move R9D, 60. The instruction writes 60 into R9D, the lower 32 bits of R9, so the R9 slot now holds parameter F. 6 loaded, 2 left 70 and 80. Under this ABI, there are 6 integer argument registers before additional integer arguments spill onto the stack. Now I want you to stop here with me, because this next part is where most people get genuinely confused, and I want to dissolve that confusion completely before we move forward. The question is, when we push the extra arguments onto the stack, what order do we push them in? Your instinct is almost certainly push 70 first, then 80. Argument 7 before argument 8. That is the natural left-to-right reading order. It is backwards, and it is not a quirk. The reason is precise, and once you see it, it clicks permanently. The stack grows downward. Every push moves RSP to a lower address, so the value you push first ends up at the higher stack address, and the value you push last ends up at the lower one. Now think about how sum8 will read these values later. Once sum8 has its own frame and its own RBP anchor, it reads stack past arguments using positive RBP relative offsets. Specifically, argument 7, value 70, parameter G, will be read at RBP plus 16. Argument 8, value 80, parameter H, will be read at RBP plus 24. RBP plus 24 is a higher address than RBP plus 16. So 80 must end up at a higher address than 70. On a downward growing stack, that means 80 has to be pushed first and 70 second. Push 80 first, it lands at the higher address. Push 70 second, it lands at the lower address. After call and the Callee prologue, that gives 70 at RBP plus 16 and 80 at RBP plus 24. That is exactly the layout this Sys-V frame expects. Push them the other way, and sum8 reads 80, where it expects G, and 70, where it expects H. Wrong values, silent corruption. The function returns the wrong answer, and you have no idea why. Line 29, push 80. The value 80 lands on the stack. See that slot appear from nothing. See RSP drop by 8. Line 30, push 70. The value 70 lands below 80. See RSP drop again. 70 at RBP plus 16. 80 at RBP plus 24. Correct for this Sys-V layout. The reverse push order produced exactly the arrangement sum8 needs in this model. These two slots belong to main. Main built them. Sum8 has not run a single instruction yet. Argument setup is complete. Step 2, call transfer. Before main jumps into sum8, the machine has to solve one problem. Once we jump into sum8, the CPU is executing instructions at sum8's address. It has no automatic memory of where it came from. The instruction pointer is just a number it points wherever it is told to point. There is no built-in return mechanism. If we do not save the return destination before we jump, that information is permanently gone. That is the entire purpose of the call instruction, not just jumping, saving first, then jumping. At the machine level, call does the two things that matter here, in this order. First, it pushes the return address onto the stack. The return address is the address of the instruction immediately after this call, not the call itself, the instruction after it. In our code, that is line 38, add RSP 16. That is where execution must resume when sum8 finishes. One operation, the moment call fires, the return address is already on the stack and execution is already inside sum8. See that slot appear? See RSP drop by 8. Look at where it sits. Above it, the two stack passed argument slots that main built. Below it, sum8's frame will be built next. This slot is the seam between caller state and callee state. The machine's written promise, when sum8 executes RET, come back to this address inside main. Step 3. Callee entry. Control has left main. Execution is now inside sum8. Look at the stack right now. 6 arguments sitting in registers, 2 on the stack, return address secured, main's frame intact, above sum8 is running. Everything it needs is in place. Step 4. Sum8's Prologue. You have seen this pattern once already with main. Same 3 instructions, same purpose. I am going to go at the same depth because the second time through is exactly where this pattern locks in permanently. 3 instructions, same Prologue pattern, different function, different frame, same mechanism, first push, RBP. Right now, RBP is still pointing at main's frame base. It has not moved since main's Prologue set it. Before we overwrite RBP to build sum8's frame, we save it. Push RBP decreases RSP by 8 and writes the current value of RBP, main's base pointer, into that new slot. See that slot appear. See RSP drop. That saved value is main's RBP. The frame pointer chain just extended one level deeper. Follow that saved value and you reach main's frame base. Follow main's saved RBP and you reach the runtime's frame base. The chain is intact, one level longer. Second move, RBP, RSP. RSP is now pointing at the saved RBP slot we just pushed. Copying RSP into RBP makes this position sum8's frame anchor. See RBP update. The anchor is now at sum8's frame base. From this moment, all of sum8's local variables will be at negative offsets from this new RBP. And the stack passed arguments G and H, which are above this anchor, now have their final RBP relative addresses confirmed. See those badges settle. RBP plus 16 is G. RBP plus 24 is H. The reverse push order we chose back in step 1 produced exactly these offsets. That decision is paying off right now. Third, sub RSP 32. Sum8 needs local storage. In this teaching build, the compiler model reserves 32 bytes. Let us look at what fills that space because the layout here is more interesting than main's. See 32 bytes of space appear. See every slot come into existence. Sum8 has 6 register passed parameters and 1 declared local variable. Here is what our teaching build does with this space. RBP minus 4 through RBP minus 24. 6 spill slots, 1 for each register passed parameter. The compiler will copy each register argument into its corresponding slot before doing any computation. Why spill to memory at all? Registers are shared across the entire CPU. If sum8 were to call another function, that function could legally overwrite our DI, RSI, and the rest. The ABI does not require callees to preserve those registers. Spilling the values into the frame guarantees they survive regardless of what happens to registers. In a highly optimized production build, the compiler might skip this and keep values in registers the whole time. But in a frame pointer teaching build, which is what we are using, the compiler spills them. RBP minus 28, the total slot. Sum8's only declared local variable. RBP minus 32, padding. Same 16-byte alignment requirement as in main. Look at the full stack on screen. 2 frames, stacked. Main's frame above. Some 8's frame below. Every slot created by a specific instruction. Nothing on this screen appeared by accident. Step 5. Sum 8's source code begins. First line, int total, same situation as result in main. This line does not create memory. The slot at RBP-28 already exists. The Prologue reserved it. This line gives that slot the name total. Uninitialized storage exists. No valid value yet. Second line. This is where sum 8 does its actual work. Total equals A plus B plus C plus D plus E plus F plus G plus H. One line of C. In this teaching build, it becomes a sequence of move and add instructions. Let us go through every single one. The strategy in this teaching build: first spill all 6 register arguments into frame slots. Then load the first value into EAX. Add each remaining value into EAX one at a time, then store the final result into total. Spill phase first. Line 5, move doored pointer, open bracket, RBP-4, close bracket, EDI. Let me break this syntax down completely because you will see it repeatedly. DWORDPTR means we are working with a 32-bit value. DWORD stands for double word, which is 4 bytes on x86. The square brackets around RBP-4 mean treat this as a memory address, not as the number itself. So this instruction says, take the 32-bit value in EDI and write it into the memory address computed by RBP-4. EDI currently holds 10, the value loaded into RDI back in main before the call. That value has been sitting in the register through the entire Prologue, unchanged. See the slot at RBP-4 receive 10. Parameter A is now safely in the frame. Now, the remaining 5 same pattern, I will move faster. Line 6 spills ESI value 20, parameter B into RBP-8. Line 7 spills EDX 30, parameter C into RBP-12. Line 8 spills ECX 40, parameter D into RBP-16. Line 9 spills R8D50, parameter E into RBP-20. Line 10 spills R9D60, parameter F into RBP-24. All 6 register arguments are now in the frame. Every spill slot has a valid value. Now the addition begins. Line 11, move EAX, D word PTRRBP-4. Loads the value at RBP-4, which is 10 parameter A into EAX. EAX is the 32-bit lower half of RAX. This is the starting value for the accumulation. RAX is now 10. Line 12, add EAX, DWORDPTRRBP-8. ADD reads the 32-bit value at RBP-8, that is 20, parameter B, and adds it to EAX, 10 plus 20. RAX is now 30. Line 13 adds RBP-12. That is 30. Parameter C, 30 plus 30. RAX is now 60. Line 14 adds RBP-16. That is 40. Parameter D, 60 plus 40. RAX is now 100. Line 15 adds RBP-20. That is 50. Parameter E, 100 plus 50. RAX is now 150. Line 16 adds RBP-24. That is 60, parameter F, 150 plus 60. RAX is now 210. 6 parameters accumulated. 2 left, and now something important happens. Line 17, add EAX, DWOR, DPTRRBP plus 16. Notice the sign change. Positive offset. This is not a local variable. This is not a spill slot. RBP plus 16 points upward past sum 8's saved RBP, past the return address, past the call boundary into main's territory, and reads the value that main pushed there. 70, parameter G. See that read happen on screen. Sum8 is reading memory that main created above the call boundary in a completely different frame. The frame boundary does not block this. The calling convention specifically arranged those slots to be reachable from exactly this offset. 210 plus 70. RAX is now 280. Line 18, add EAX DWOR DPTRRBP plus 24. Reads RBP plus 24. That is H value 80, also in mains territory. 280 plus 80. RAX is now 360. All 8 values accumulated. The result is 360. Line 19 moved doored pointer RBP minus 28 EAX. Stores the final result 360 from EAX into the total slot at RBP minus 28. See total update on screen, 360. First valid value written into this frame. The function body is complete. Step 6, the epilogue. This is the payoff of the entire lecture. In this frame-based model, what is about to happen is the prologue unwinding in reverse order. Watch the stack unwind. But first, before the frame is destroyed, Sum8 has to deliver its result to main. It cannot leave 360 in the total slot. That slot is about to cease to exist. How does a function return an integer value in the System-V ABI 64ABI? Through RAX. RAX is the designated return value register. That is its role in the contract. Line 20, MOV EAX, DWOR, DPTRRBP, minus 28, loads total 360 from the frame into EAX, the lower 32 bits of RAX. 360 is now in RAX. Safe. The frame can be destroyed, and that value survives in the register. Now the tear down. 3 steps, reverse order. First move RSP, RBP. RBP is pointing at Sum8's frame base, just at the saved RBP slot. Copying RBP into RSP collapses everything below the frame base, all 6 spill slots, the total slot, the padding released in one instruction. See RSP snap upward. See every local slot vanish simultaneously. The entire storage area of Sum8's frame is gone. RSP is now pointing at the saved RBP slot. Second pop RBP. Pop RBP reads the value at the current top of the stack, which is the saved RBP slot containing main's base pointer, writes it back into RBP, and then increases RSP by 8. See the saved RBP slot disappear. See RBP snap back to main's frame base. See RSP move up by 8. Main's base pointer is restored. RBP is now pointing at the exact same address it held before Sum8 was ever called. From main's perspective, RBP never changed. Sum8's frame is completely gone. RSP is now pointing at the return address, the slot that call pushed back in Step 2. Step 7, RET does one thing, pops the value at the top of the stack, the return address, and loads it into the instruction pointer. Execution jumps to wherever that address points. See the return address slot vanish. See RSP increase by 8. The machine kept its promise. Sum8 is gone. Its frame no longer exists. The stack has unwound. 360 is in RAX. Waiting. Execution is back in main. Line 38. Line 38 add RSP 16. This cleans up the 2 stack passed argument slots, G and H, that main pushed before the call. Adding 16 to RSP moves it upward past both 8-byte slots, releasing them. See G and H disappear. See RSP move up. Those slots are gone. Line 39, move doored pointer RBP minus 4 EAX. Reads the return value from EAX 360 and writes it into main's local slot at RBP minus 4. That slot is result. See result update. 360. The uninitialized marker is gone. A valid value is finally in that slot. This is the moment the function call completes its purpose. Last line of main, return 0, same mechanism. Return value into RAX. Epilogue tears the frame down, RET fires. Line 40 move, EAX, 0. The return value of main is 0. The exit code reported to the operating system. 0 means success. Into EAX, line 41, move RSP RBP. Collapses main's local storage. The result slot and padding are gone. Line 42, pop RBP. Restores the runtime startup code's base pointer. Main's saved RBP slot is gone. RBP is back to where the runtime left it. Line 43 ret. Pops main's return address. Execution jumps back into the runtime startup code. Main is done. The stack is empty. Everything has unwound. The runtime does its cleanup and makes a system call to end the process. Let us look at what we just covered. We applied the 7-step lifecycle twice. Once to main, once to sum8. Same map both times, in full detail. In our frame pointer teaching build, the Prologue built each frame in 3 steps. Save the old RBP, set the new RBP, subtract from RSP. The Epilogue tore each frame down in 3 reverse steps. Move RSP back to RBP, pop RBP, then RET. In this Sys-V walkthrough, the calling convention placed 6 integer arguments into registers and 2 onto the stack in reverse push order, because the stack grows downward and the positive RBP relative offsets in the receiving frame demand that arrangement. Every move and add instruction in sum8's body executed one at a time. 6 spills into the frame, a starting load into EAX, 6 additions from the frame, 2 additions from above the call boundary reaching directly into main's territory, and a final store into total. Call saved the return address before transferring control. RET popped that saved address and transferred control back to it. Every slot that appeared on that stack had a reason. Every register change had a cause. Every step followed directly from the one before it. That is what a stack frame actually is. You now know how stack frames are built, used, and destroyed, but not all memory disappears when a function returns. In the next lecture, we move to the heap.